Have you ever wondered why a javelin thrower releases at a specific angle, not straight up, not flat, or why a race car driver brakes before a sharp curve, not during it, or how a satellite can orbit the Earth indefinitely without falling down or flying away into space? These aren't random choices. They're governed by precise, predictable laws of physics, the laws of motion in a plane. The illustrations show a javelin thrower, a race car, and a satellite in orbit. From a basketball arching through the air to a planet sweeping around the sun, the same principles apply. That's the story this video tells. Here's the map for everything ahead. We start with fundamental vectors: position, displacement, velocity, and acceleration. The mathematical language for describing any 2D motion. You can see those ideas previewed in the vector diagrams here. Then we move into projectile motion, trajectories, ranges, and maximum heights, captured in the parabolic arc diagram. After that, circular motion, both uniform, where speed stays constant but direction keeps changing, and non-uniform, where speed itself varies, shown in the two circular diagrams. And finally, real-world applications: banked roads, roller coasters, bridges. By the end, you'll understand the forces that keep you on the road and keep satellites in orbit. Motion in a plane is simply motion in two dimensions. Two directions track simultaneously. Two examples make this concrete. A football kicked into the air follows a parabolic path, as the first diagram shows. A stone whirled on a string sweeps through a circle, with the inward force and tangential velocity labeled in the second diagram. Both involve movement along two directions at once, which is exactly what distinguishes 2D motion from 1D straight-line motion. To analyze it, we place an origin at a reference point and set up two coordinate axes, x and y. The comparison diagram at the bottom shows why one axis simply isn't enough. Moving into our first core concept, we define the position vector. It is technically a vector that extends from a specific reference point to the exact point where a particle is currently located. In this first diagram, you see vector r drawn from origin O to point P. A more detailed view shows how we resolve this into two dimensions. The position vector r equals xi hat plus y j hat, where I hat and j hat are unit vectors that define the x and y axes. As the formula shows, the vector is simply the sum of its horizontal and vertical components. To find the vector's direction, we look at the orientation relative to the axes. We define the direction using angle theta, where the tangent of theta is equal to the ratio of the y-coordinate over the x-coordinate. This right triangle diagram visualizes that relationship clearly, showing base x and height y. This concept extends naturally into three dimensions. In 3D space, we simply add a z component along the k-hat direction. This final three-dimensional diagram illustrates how the vector identifies a point's position within a volume. The displacement vector differs from the position vector. It doesn't measure where you are, it measures how far and in what direction you've moved from one point to another. Think of it as the straight line shortcut from starting point A to ending point B, regardless of the path you actually took. The diagram shows point A at coordinates x1, y1, with position vector r1, and point B at x2, y2, with position vector r2. The displacement delta r is the arrow from A to B. Its magnitude is the square root of delta x squared plus delta y squared. The direction satisfies the tangent of theta equals delta y over delta x. In 3D, the formula adds a z component along k-hat. Building on our look at displacement, we now define the average velocity vector. Generally, the velocity of an object in motion is the ratio of its total displacement to the time interval as it moves between points. More specifically, average velocity is defined strictly as this displacement over time ratio. Looking at the formulas, average velocity, VAV, equals the change in position vector r divided by delta t, which expands to r2 minus r1 over t2 minus t1. We can express this in component form as well. Here, VAV equals delta x over delta t in the I direction, plus delta y over delta t in the j direction. giving us velocity components Vx and Vy. In this vector diagram, you can see the resultant velocity vector in the coordinate plane resolved into these horizontal and vertical components. To determine the vector's direction, we use the standard triangular rule. We calculate the direction angle theta using the expression tangent of theta equals the vertical velocity component delta Vy divided by the horizontal component delta Vx. Instantaneous velocity is what average velocity becomes as the time interval shrinks to 0. Mathematically, v equals the limit of delta r over delta t as delta t approaches 0, the derivative dr over dt. The diagram illustrates this precisely. As points P1 and P2 move closer together, the displacement vector rotates toward the tangent of the curved path. At the limit, the instantaneous velocity is exactly along that tangent. In component form, v equals dx over dt times I hat plus dy over dt times j hat. The magnitude of the velocity is the square root of the x component of velocity squared plus the y component of velocity squared. And the direction satisfies the tangent of theta equals the y component of velocity over the x component of velocity, as the vector diagram shows. Acceleration is the rate of change of velocity. Average acceleration equals delta v over delta t, the change in the velocity vector divided by the corresponding time interval. In 2D, this has an x component and a y component. Average acceleration equals the change in the x component of velocity over delta t times I hat, plus the change in the y component of velocity over delta t times j hat. The component form is average acceleration equals the x component of average acceleration times I hat, plus the y component of average acceleration times j hat. The vector diagram shows these components and the resultant in the coordinate plane. Magnitude is the square root of the x component of average acceleration squared plus the y component of average acceleration squared. And the right triangle diagram confirms this. The direction angle theta with the x-axis satisfies the tangent of theta equals the y component of average acceleration over the x component of average acceleration. Instantaneous acceleration is the limiting value of average acceleration as the time interval approaches 0, the derivative of velocity, a equals dv over dt. The first diagram shows this geometrically. As 2 points on the path get closer, the change in velocity vector delta v converges to the instantaneous acceleration direction at that point. In component form, a equals the x component of acceleration times I hat plus the y component of acceleration times j hat, shown in the second vector diagram with both components laid out. The direction of instantaneous acceleration makes an angle theta with the x-axis, where the tangent of theta equals the y component of acceleration over the x component of acceleration. Note that acceleration doesn't have to point along the velocity. In curve motion, they're typically in different directions. Uniform acceleration means the velocity vector changes by the same amount in every equal time interval. The first diagram shows velocity vectors v1, v2, and v3, equally spaced in time, with equal changes between them. The trajectory diagram shows how this constant push produces a curved path. From the definition of average acceleration, we write a equals v minus the initial velocity over t, which rearranges to the first equation of motion. V equals the initial velocity plus a times t. The diagram illustrates this vector addition of the initial velocity and at to get v. Breaking into rectangular components gives 2 independent equations. Along x, the x component of velocity equals the initial x component of velocity, plus the x component of acceleration times t. Along y, the y component of velocity equals the initial y component of velocity, plus the y component of acceleration times t. 2 separate 1D problems. Now we derive the position vector. Let the initial position be the position at time 0 and r the position at time t, with velocities the initial velocity and v at those instants. Under constant acceleration, average velocity equals the initial velocity plus v, divided by 2. Displacement is average velocity times time. R minus the initial position equals the quantity v plus the initial velocity over 2 multiplied by t. The diagram shows this displacement as a vector from the initial position to r. Substituting v equals the initial velocity plus a times t into the displacement equation and simplifying, we get r minus the initial position equals the initial velocity times t plus 1/2 at squared. Rearranging gives the second equation of motion. R equals the initial position plus the initial velocity times t plus 1/2 at squared. To find the path of a particle in 2 dimensions, we express the position vector in rectangular components. We begin with the general vector equation of motion, expressing position r as the sum of initial position, initial velocity times time, and the acceleration term, all broken into I hat and j hat components. The coordinate diagram shows the position vector r from the origin to a point x, y in the xy plane. By equating the coefficients of the unit vectors, we can separate the motion into its orthogonal parts. Along the x-axis, the position x is given by the initial x position plus the initial x velocity component times t, plus 1/2 the x acceleration times t squared. Similarly, along the y-axis, the position y is equal to the initial y position plus the initial y velocity component times t plus 1/2 the y acceleration times t squared. This leads us to the foundational principle of kinematics. Any motion in a plane can be treated as 2 separate, simultaneous, one-dimensional motions with constant acceleration along perpendicular directions. This is illustrated by the parabolic trajectory, where the total velocity vector is simply the result of independent horizontal and vertical components acting at once. So far, we've built the mathematical framework. Now we put it to work on one of the most important topics in classical mechanics. When an object is thrown at angle theta from the horizontal, any angle except straight up at 90 degrees, it follows a curved path called a trajectory. The object is a projectile, and this is projectile motion. The small diagram shows the launch setup. The large diagram reveals the full picture. Initial velocity u splits at point A into horizontal component u cosine theta and vertical component u sine theta. The projectile arcs upward to peak B, then descends to landing point C. Total horizontal distance is labeled r, and maximum vertical height is labeled h. From those two components, every formula follows. If an object is thrown with speed u at angle theta from the horizontal, the velocity vector diagram shows the initial decomposition. Horizontal component u cosine theta and vertical component u sine theta. Here's what makes projectile motion so elegant to analyze. The horizontal component u cosine theta remains exactly constant throughout the entire flight. There is no horizontal force acting, so horizontal acceleration is 0. The diagram confirms this. Equal horizontal arrows all the way across. But the vertical component u sine theta decreases steadily due to gravity, as the second diagram shows. It reaches 0 at the highest point, then reverses. At the peak, velocity is purely horizontal at u cosine theta, and gravity acts at exactly 90 degrees to that velocity. Building on our trajectory analysis, let's derive the 2 core projectile formulas for time and height. First, the time of flight, capital T. The left diagram illustrates this duration, representing the entire period the object remains airborne from launch to landing. Formally, it is defined as the total time for which the projectile remains in the air. Mathematically, the time of flight t equals 2u sine theta divided by g, which directly scales with the initial vertical velocity component. Next, we consider the maximum height, capital H. This second diagram focuses on the peak of the arc, where the vertical velocity momentarily drops to 0. This is defined as the maximum vertical height covered by the projectile during its flight. Applying kinematic equations to this peak point gives h equals u squared sine squared theta divided by 2g, showing how height depends heavily on the launch angle and initial speed. Next, we analyze the formulas for projectile range. Horizontal range, denoted by capital R, is formally defined as the maximum horizontal distance covered by the projectile from its launch point to its landing. By combining our previous results for velocity and time, we derive the general formula. R equals u squared times the sine of 2 theta, all divided by gravity g. This compact equation highlights the significance of our variables. Range depends explicitly on the square of the initial speed and the launch angle theta. We can see this full horizontal sweep clearly in the diagram, where r represents the displacement along the landing plane. At the highest point of its flight, the projectile carries only horizontal velocity, u cosine theta. So linear momentum there is m times u cosine theta, and kinetic energy is 1/2 m times u cosine theta, all squared. The vertical component contributes nothing since it is 0 at the peak. The diagram confirms this with just the horizontal arrow at point B. After time t from launch, horizontal displacement is x equals u cosine theta times t, constant velocity, simple. But vertical displacement has two terms, y equals u sine theta times t, minus 1/2 g times t squared. The first term carries the projectile upward. The second is gravity pulling it back, growing stronger as t increases. Now eliminate time to get the path equation in terms of x and y alone. From horizontal displacement, x equals u cosine theta times t, we solve for t equals x over u cosine theta. Substituting into the vertical displacement equation and simplifying gives the path equation. Y equals x the tangent of theta minus g over 2u squared cosine squared theta times x squared. The graph shows this curve. The form matches y equals ax minus bx squared, which is a downward opening parabola. This confirms what every diagram has shown. Every projectile traces a parabolic path. The parabolic nature isn't an approximation for small angles or low speeds. It's the exact mathematical consequence of constant horizontal velocity and constant vertical acceleration. The instantaneous speed at time t during flight is the magnitude of the velocity vector, combining both components. That works out to the square root of u squared plus g squared t squared minus 2ugt sine theta. At t equals 0, or at landing where height returns to 0, this simplifies back to u, confirming the object returns to its launch speed when it lands. At the lowest point of the trajectory, kinetic energy is 1/2 mu squared, using the full initial speed u. And linear momentum at that lowest point is simply the friction coefficient. Both results use the full launch speed because the vertical velocity component has the same magnitude at landing as at launch. It's been reversed by gravity, but not reduced. 3 more important facts. The acceleration of a projectile is constant throughout the entire flight, always equal to g, always pointing vertically downward. The horizontal component of acceleration is 0, and the vertical component is g, unchanging from launch to landing. The angular momentum of the projectile about the launch point at height h equals m times u cosine theta times h, the horizontal momentum component multiplied by the current height. In an angular projection, the angle between the velocity vector and the downward acceleration of gravity changes continuously. It starts close to 0 on the steep initial rise, passes through 90 degrees at the peak when velocity is purely horizontal, and continues increasing to approach 180 degrees as the object descends steeply. 2 elegant geometric results follow from the parabolic path. The projectile attains its maximum height exactly when it has covered half the horizontal range, at position r over 2. This confirms the perfect left-right symmetry of the parabola. The ascent and descent are mirror images. The second result, when the maximum range is r, achieved at 45 degrees, the corresponding maximum height is exactly r over 4, 1/4 of the range. These are not approximations or special cases. They fall directly from dividing the maximum height formula, h equals u squared over 4g, by the maximum range formula, r equals u squared over g, giving h equals r over 4. clean and exact. From r equals u squared sine 2 theta over g, the range is maximum when sine 2 theta equals 1, meaning 2 theta equals 90 degrees. So the optimal launch angle is 45 degrees. Maximum range is then u squared over g. The first graph confirms this optimal 45-degree parabolic trajectory. But there's a hidden symmetry in the sine 2 theta term. Since sine 2 theta equals sine 180 minus 2 theta, angles theta and 90 minus theta, complementary angles, give identical ranges. Launching at 30 degrees and launching at 60 degrees both land at exactly the same horizontal distance. The second graph shows both trajectories starting from the same point and landing at the same point, with very different heights in between. A subtle variation. The projection angle theta is measured from the vertical y-axis, not the horizontal. The diagram shows initial velocity u making angle theta with the y-axis, which means the angle with the horizontal is 90 minus theta. The components swap accordingly. Horizontal component becomes u sine theta. Vertical component becomes u cosine theta. The formulas shift to match. Time of flight is now t equals 2 u cosine theta over g. Maximum height is h equals u squared cosine squared theta over 2g. Horizontal range remains r equals u squared sine 2 theta over g, the same formula as before, since sine 2 theta is symmetric. The equation of path becomes y equals x cot theta minus gx squared over 2 u squared sine squared theta. Now a new class of problems. Projectiles launched from a height. Case 1 is the simplest. Imagine standing on a tower of height h and throwing a stone perfectly horizontally, straight out in front of you. The diagram shows this setup. The stone leaves the tower with horizontal velocity u and follows a parabolic arc curving downward to the ground at horizontal distance x. The initial conditions are clear. Vertical velocity at launch equals 0, no upward or downward component at all, and horizontal velocity equals u. From the moment of release, gravity accelerates the stone downward while it continues forward at constant horizontal speed. The path curves smoothly because these two motions are independent and simultaneous. For horizontal launch from height h, time of flight depends only on the height, not the horizontal speed. T equals the square root of 2h over g. The horizontal range is then x equals u times t. After t seconds of flight, vertical velocity has grown from 0 to the y component of velocity equals g times t, building steadily from rest. Total velocity magnitude at time t is the square root of u squared plus g squared t squared, combining the constant horizontal and growing vertical components. The velocity vector diagram shows horizontal component, the x component of velocity, equals u, and vertical component, the y component of velocity, at angle phi below horizontal, where the tangent of phi equals gt over u. The equation of path is y equals g over 2u squared times x squared, a parabola, as the graph shows. Case 2. The projectile is launched from a height, but angled downward at angle theta below the horizontal, like rolling a stone off a cliff at a downward angle. The diagram shows the cliff of height h, with initial velocity u pointing diagonally downward at angle theta. Initial conditions split into horizontal component u cosine theta pointing forward, and vertical component negative u sine theta pointing downward. Negative because the vertical motion already begins in the downward direction at launch. This means the stone never rises above the launch point. It curves downward immediately, hitting the ground sooner than a horizontal launch from the same height. The trajectory is a compressed parabola compared to the upward angle cases. For downward launch from height h at angle theta below horizontal, time of flight comes from a quadratic equation. The result is t equals negative u sine theta over g, plus or minus the square root of 4u squared sine squared theta plus 8gh, all divided by 2g. Take the positive root, that is the physical time when the object hits the ground. The diagram confirms this trajectory. Horizontal range is then x equals u cosine theta times t. Vertical velocity at time t is the y component of velocity equals u sine theta plus g times t. It starts at u sine theta downward and grows further in the same direction. Total velocity is the square root of u squared plus g squared t squared plus 2ugt sine theta. The positive cross term appears because vertical velocity and gravity are already aligned from the start. Case 3 is the most complete launch scenario. The projectile is thrown upward from a height at angle theta above the horizontal. Unlike the previous two cases, the object first rises above the launch point, reaches a peak, then falls all the way down to the ground, well below the launch height. The picture hints at this upward first trajectory. Initial conditions: horizontal component u cosine theta and vertical component u sine theta upward, both positive. The diagram shows the full arc, starting from height h, peaking above that level, then descending to horizontal distance x on the ground. This case has the longest time of flight of all three scenarios because the object gains additional height before beginning its final descent. For upward launch from height h at angle theta, the time of flight equation is quadratic. T equals u sine theta over g, plus or minus the square root of u squared sine squared theta over g squared plus 2h over g. Always take the larger positive root, that is, the actual landing time when the object finally reaches the ground below. Horizontal range is x equals u cosine theta times t. Vertical velocity at time t is the y component of velocity equals negative u sine theta plus g times t. It starts negative because initial vertical velocity was upward, then reverses sign as gravity acts. Total velocity magnitude is the square root of u squared plus g squared t squared minus 2ugt sine theta. The negative cross term reflects the opposition between upward launch and downward gravity. Now the most complex projectile scenario. Launched from a surface tilted at angle beta from horizontal, with the object thrown at angle alpha from the horizontal. The key is to resolve everything along and perpendicular to the inclined surface, not the usual horizontal and vertical. Velocity along the plane at launch is u cosine alpha minus beta. Velocity perpendicular to the plane is u sine alpha minus beta. Gravity also resolves into two components: g sine beta acting along the plane pointing down the slope, and g cosine beta acting perpendicular to the plane pressing into the surface. With this setup shown clearly in both diagrams, the inclined plane problem reduces to familiar 1D kinematics in a tilted coordinate frame. With those components established, the formulas follow the same structure as flat ground projectile motion, with g replaced by g cosine beta for the perpendicular direction and g sine beta for the along plane direction. Time of flight is t equals 2 u sine alpha minus beta divided by g cosine beta. Maximum height above the inclined surface is h equals u squared sine squared alpha minus beta divided by 2g cosine beta. Range along the incline is r equals 2u squared times sine alpha minus beta times cosine alpha, all divided by g cosine squared beta. Every formula mirrors the flat ground structure, with the incline angle woven into both numerator and denominator. The angle beta effectively reduces the perpendicular gravitational component. The range along the inclined surface is maximized when the launch angle alpha equals 45 degrees plus beta over 2. The optimal angle shifts upward by half the slope angle compared to flat ground. For an upward slope, maximum range is u squared divided by g times 1 plus sine beta. For a downward slope, maximum range is u squared divided by g times 1 minus sine beta. Since 1 minus sine beta is smaller than 1 plus sine beta, launching downhill always gives greater range than launching uphill at the same speed. And just like flat ground, complementary launch angles on the incline, alpha and 90 minus alpha plus beta, produce identical range. The diagram shows two different trajectories landing at exactly the same point on the slope. So that covers projectile motion, objects moving in open parabolic paths. Now we shift to something fundamentally different: objects moving in closed curves. Circular motion is the movement of an object along a circular path. Two distinct types exist. In uniform circular motion, speed is constant, but the direction of velocity keeps changing at every instant, meaning there is always acceleration, even at constant speed. The diagram shows velocity vectors tangent to the circle at 4 positions, with centripetal force and centripetal acceleration both pointing inward. In non-uniform circular motion, the speed itself changes around the path, as the varying length velocity vectors illustrate. One important distinction: spinning on your own axis is rotation, not circular motion. The object stays in place rather than traveling along a path. To describe circular motion precisely, we shift from linear variables to angular ones. Angular displacement, delta theta, is the angle swept by the position vector at the center as the object moves from one point to another. The diagram shows initial position P1 and final position P2 on the circle, with angle delta theta between the two radii and arc length delta s along the path. The relationship is delta theta equals delta s over r, where r is the radius. SI unit is the radian. 1 radian corresponds to an arc length equal to the radius. So a full circle of circumference 2 pi r corresponds to exactly 2 pi radians, a clean and natural unit system for rotation. Angular velocity, omega, is the rate at which angular displacement changes with time. The formula is omega equals delta theta over delta t. It is a vector quantity, direction given by the right-hand rule along the axis of rotation, with SI unit radians per second. The first diagram shows the object sweeping through angle delta theta in time delta t, with a curved arrow indicating the direction. The critical link between angular and linear quantities is v equals r times omega. At radius r from the center, linear speed equals the radius times the angular velocity. This means points farther from the center move faster in terms of linear speed, even while sharing the same angular velocity as points closer in. Moving forward to slide 36, we define angular acceleration. To begin, angular acceleration is the rate at which the angular velocity changes over time. Visually, the first diagram tracks the difference between initial and final angular velocity vectors to determine the acceleration's direction. Key properties for this quantity include its SI unit of radians per second squared and a dimension of t to the negative 2. Mathematically, alpha is defined as the limit of delta omega over delta t, or the second derivative of angular displacement with respect to time. Beyond the definition, we must consider several critical relations between variables. One fundamental formula links linear and angular worlds, stating that centripetal acceleration equals the radius times the angular acceleration. This connection is shown geometrically in the second diagram, where the acceleration vector points directly toward the center. Furthermore, in specific contexts, alpha can be expressed as the linear speed squared divided by the radius. This final diagram helps visualize how tangential velocity and acceleration relate to the circular path. Our focus now shifts to non-uniform horizontal circular motion. Looking at the dynamics involved, we see that in this specific type of motion, the magnitude of the velocity is no longer constant and changes over time. The coordinate diagram illustrates a point on the circular path where multiple acceleration vectors originate. Specifically, we must consider 2 distinct accelerations, acting simultaneously. First, the centripetal or radial acceleration, AC, acts toward the center, while second, the tangential acceleration, AT, acts along the tangent to the path. For the combined effect, we calculate the resultant acceleration. This total acceleration, A, is the vector sum, calculated as the square root of the quantity v squared over r, all squared, plus the quantity r times angular acceleration alpha, all squared. Finally, the direction of this resultant is given by the tangent of angle phi, which equals tangential acceleration divided by centripetal acceleration, or r squared times alpha divided by v squared. Circular motion obeys 5 kinematic equations that perfectly mirror the linear equations of motion. Equation 1. Omega equals omega 0 plus alpha times t. Angular velocity changes linearly with time under constant angular acceleration. Equation 2. Theta equals omega 0 times t plus 1/2 alpha t squared. Equation 3. Omega squared equals omega 0 squared plus 2 alpha theta. Equation 4. Theta for the tth second equals omega 0 plus 1/2 alpha times the quantity 2t minus 1. In equation 5, theta equals omega plus omega 0 over 2 times t. The diagram shows the setup with initial angular velocity omega 0 and final angular velocity omega after angular displacement theta. Variables. Omega 0 is initial angular velocity. Omega is final angular velocity. Alpha is angular acceleration. Theta is angular displacement. And t is time. Here's a result that surprises many people the first time they encounter it. In circular motion, even at perfectly constant speed, there is always acceleration. The reason is that velocity is a vector, and its direction is continuously changing even when its magnitude is fixed. This acceleration is called centripetal acceleration, also called radial acceleration, and its direction is always toward the center of the circular path. The diagram shows the centripetal acceleration as an inward arrow at a point on the circle, while velocity v is tangent and perpendicular to it. The formula is centripetal acceleration equals v squared over r, which also equals r times omega squared. Units are meters per second squared, and it is a vector always directed inward. Next, we examine centripetal force. The diagram on the left illustrates a body in circular motion, where a force vector F sub c points from the object along radius r toward the center. Formally, we define it as the force that must act on any body to maintain a circular path. This force is strictly directed along the radius toward the center of the circle. We calculate its magnitude using the formula. Centripetal force equals mv squared over r, which is also equivalent to mr omega squared. An essential property to remember is the work done by this force. The total work done by the centripetal force is always exactly zero. To understand the reason, consider the geometric relationship between the acting force and the motion. The centripetal force and the instantaneous displacement are always at right angles, or 90 degrees, to each other. As shown in the final diagram, because the force F is perpendicular to the tangential displacement S, no work is performed. Centripetal force is not a new fundamental force. It is a role that different physical forces play depending on the situation. When planets orbit the sun, gravity between planet and sun provides the centripetal force, shown in the first diagram with a gravitational arrow pointing from Earth toward the sun. When an electron orbits the nucleus, the electrostatic attraction between electron and nucleus plays that role, as the second diagram shows. A car navigating a curved road relies on friction between tires and road to provide the inward force, illustrated in the third diagram. And when you swing a stone on a string in a circle, it is the tension in the string that acts as the centripetal force. Same physics, 4 completely different physical mechanisms. While we have focused on inward forces, we must also consider centrifugal force. We can define this specifically as a radially directed outward force that acts on a body in circular motion, but only as observed by a person moving along with that body. It is always equal in magnitude, yet exactly opposite in direction to the centripetal force. The diagram illustrates this relationship, showing the blue centrifugal force vector pointing directly away from center O, while the inward tension vector T maintains the circular path. This is why we call it a non-inertial frame pseudo-force. As an important note, remember that centrifugal force does not actually act on a body when viewed from a stationary inertial frame. Instead, it arises as a pseudo-force solely within non-inertial frames of reference. When a car turns on a flat, unbanked road, the centripetal force comes entirely from static friction between the tires and road surface. The diagram shows the friction force arrow pointing inward toward the center of the curve. For a safe turn without sliding, the condition is the coefficient of static friction must be greater than or equal to v squared over r times g. Rearranging gives the maximum safe turning speed as the square root of the friction coefficient times r times g. Exceed this speed and friction cannot provide enough centripetal force. The car slides outward toward the edge. This is why sharp curves carry lower speed limits, and why wet or icy roads, which reduce the coefficient of friction, are so dangerous at the same speeds that would be safe on dry pavement. Moving on to slide 44, we examine circular turning through banking alone. The diagram illustrates a road tilted at angle theta, where the normal force N is perpendicular to the surface. In a banking-only scenario, the entire centripetal force is derived from the horizontal component of this normal force. The formula for the ideal safe speed v is the square root of r times g times the tangent of theta. Let's look at the vehicle dynamics when speeds vary from this ideal. If the velocity v is less than the square root of rg tangent theta, the centripetal force is too strong for the speed. Consequently, the vehicle moves inward and slides down the banked slope. This motion is shown in the first small diagram with the green arrow. Conversely, if v is greater than the square root of rg tangent theta, the car lacks sufficient inward force. This causes the vehicle to move outward and slide up the bank. The final diagram depicts this outward skid with the pink arrow. In real-world roads, friction and banking both contribute simultaneously to the centripetal force. Banking tilts the surface so that the normal force has an inward component. Friction adds additional inward force when the speed exceeds the ideal banked speed, or prevents inward sliding when speed is below it. Together, they allow a safe speed range that is much wider than either mechanism alone. The diagram shows all forces acting. Normal force, N perpendicular to the banked surface, weight, M, G downward, static friction up the slope, and the resulting horizontal centripetal force. Maximum permissible speed is the square root of r times g times the quantity tangent theta plus the coefficient of static friction, divided by 1 minus the coefficient of static friction times the tangent of theta. A cyclist taking a turn leans inward, and this is not instinct or preference, it is physics. When the cyclist tilts at angle theta from vertical, the normal reaction force N from the ground tilts with them. The vertical component N cosine theta balances the weight mg, preventing the cyclist from toppling. The horizontal component N sine theta acts as the centripetal force needed to maintain the circular path. Setting up both equations and dividing eliminates N entirely, giving the tangent of theta equals v squared over r times g. The faster the speed or the tighter the turn radius, the larger the required lean angle. Lean too little and centripetal force is insufficient, and the cyclist slides outward. The diagram labels all four quantities, N, theta, centripetal component, and mg. A conical pendulum has a bob attached to a string fixed at point O, whirled horizontally in a circle. The string sweeps out a cone, making angle theta from the vertical, which is where the name comes from. The diagram shows the full force analysis. Tension T in the string, its vertical component T cosine theta balancing the weight mg, and its horizontal component T sine theta providing the centripetal force for the circular motion. Setting up these two equations and solving gives angular speed omega equals the square root of g times the tangent of theta over r, where r is the radius of the horizontal circle. The time period is t equals 2 pi times the square root of L cosine theta over g, where L is the length of the string. The death well, also called a rotor, is one of the most dramatic demonstrations of circular motion physics. A cyclist rides along the inside of a vertical cylindrical wall, or a person stands pressed against the wall of a spinning drum. Gravity pulls them straight down. The wall pushes them inward with normal force N, and that normal force acts as the centripetal force, keeping them moving in the circle. Friction between the person and the wall points upward, exactly balancing gravity and preventing them from sliding down. The diagram shows these forces. N pointing toward the center, friction pointing up, and mg pointing down. For the system to work, the minimum safe speed must satisfy v equals the square root of g times r over the friction coefficient. Motion in a vertical circle is more complex because gravity's role changes continuously around the loop. Going up, gravity opposes motion and reduces speed. Coming down, gravity assists and increases speed. The diagram shows a particle in a vertical circle of radius r, with velocity and tension labeled at 3 key positions. The critical question is, what minimum speed is needed to complete the loop without the string going slack? At the top, point C, minimum speed is the square root of g times r. Any slower and tension drops to 0, losing contact. At the horizontal position B, minimum speed is the square root of 3gr. And at the bottom, point A, to ensure the object makes it around, minimum speed there must be the square root of 5gr. The tension in the string throughout a vertical loop varies dramatically with position. At the top of the loop, point C, when moving at the minimum speed, the tension drops all the way to 0. Gravity alone provides the full centripetal force, and the string is momentarily slack. At the horizontal position B, the tension is 3 mg, 3 times the weight of the object. And at the very bottom, point A, where the object is moving fastest, and gravity must be overcome to produce upward centripetal force, the tension reaches 6 mg, 6 times the weight. The diagram shows all 3 values together. Maximum string stress occurs at the bottom of the loop, not the top, a counterintuitive but important design fact for any loop structure. A vehicle driving over the crest of a convex, hump-shaped bridge is undergoing circular motion. The center of curvature lies below the road, so centripetal force must point downward toward that center. At the top of the hump, gravity mg acts downward, and normal reaction N1 acts upward. The net downward force provides centripetal force. mv squared over r equals mg minus N1, rearranging to N1 equals mg minus mv squared over r. Notice that N1 is less than the vehicle's actual weight, mg. The vehicle feels lighter than it truly is. The faster the vehicle travels, the smaller N1 becomes. At a critical speed where v squared equals rg, N1 drops to 0, and the vehicle loses contact with the road surface entirely. At the dip of a concave, hollow bridge, the opposite situation applies. The center of curvature is above the road, so centripetal force must point upward. At the lowest point, normal reaction N2 acts upward, and gravity mg acts downward. The net upward force provides centripetal force. mv squared over r equals N2 minus mg, giving N2 equals mg plus mv squared over r. The vehicle feels heavier than its true weight. The faster it goes through the dip, the heavier it feels. Both effects, lighter on humps and heavier in dips, are the same physics. Speed through a curve changes the apparent weight. One final note. Overturning of vehicles happens when the inner wheel lifts off first due to torque from the centripetal force and speed combination. This concludes our comprehensive summary of motion in 2 dimensions. We started with position vectors r that locate a point at an angle theta in a coordinate system. These position vectors formed our foundation. Then we explored the projectile arc, where an initial velocity v0 is split into components. This projectile arc shows that horizontal and vertical motions are independent. Next, we examined uniform circular motion, where the velocity vector is always tangent to the circle. In uniform circular motion, centripetal acceleration and force point directly toward the center. We also analyzed the dynamics of vertical loops, tracking the changes in normal force and weight at different positions. Understanding vertical loops clarifies how apparent weight changes during curved motion. Collectively, these key takeaways show how we have journeyed from basic vectors to complex loops. That was Physcribe. If this breakdown helped you see physics in a new light, subscribe to Physcribe. We are here to help you master the universe, one equation at a time. And we will see you in the next video. Stay tuned for more physics. Remember, We master the universe, one equation at a time.